Hello, y'all. How you doing? So here today talking about some electromagnetism. I have one of my textbooks there already in case I need it. I have my pad here. So my plan is to sort of start with some basics and lead with whatever questions you all might have if anybody shows up live. And so I'll see how it goes. So far we've had at least one person show up. So I expect at least one will show up. And uh, and then I'll just see whatever questions you have. But hey, what's going on, Captain? Doing good. Thanks for showing up. How have you been? What's going on, Banso? It's been a while. Glad to see you. So I'll go ahead and talk about some EM, and I'm also in Discord. If anybody wants to join Discord, that's the screen share that's going on right now. So if anybody wanted to join Discord, you could join at the link that's scrolling on the top. Glad you're doing well. And what I'll do is just start with some basic electromagnetism concepts, or if you all have anything that you want to talk about in particular, let me know in the electromagnetism realm. So I have understanding up to basically the uh, you know, sophomore, junior, undergraduate level. Right now I'm a senior, so I'm learning the senior stuff. I have some idea about it, but the basic electromagnetism stuff I have a handle on, so you can let me know. As a matter of fact, let me see if this chat is working. Oh, well, let me take a moment and get the chat thing worked out. I forgot to do that actually. So I can show the chat sometimes. So let me take a look here. And perhaps you all can see if anything comes up on your mind more at the moment. Let me see if this is working properly. So I'll show chat. I believe all I have to do is copy this link. There you go. Awesome. So once in a while, I'll pop in and show the chat there, as long as I remember to unshow it when I'm not actually talking about the chat. So EM. An interesting thing about electromagnetism is initially, hey, what's going on, Lisa? Good to see you. Initially, it was basically different subjects at first. Like we thought that electric field was one thing, magnetism was another thing, and then light was another. Of course, we had many different ideas of light. Oh, I've been doing good, Lisa, hanging in there. A lot of studying, starting to apply for grad school. So that's slightly harrowing doing research on that. What's going on, Dark Like Mike? Good to see you. So busy, but always enjoy coming in and talking and getting some science talk in instead of some derp in. And I thank you all for chatting and letting me know you're here. And so EM. But along the way, what happened was we pretty much learned and understood that um, these things are correlated in a very direct way. So, an interesting thing is one of the things that was highlighted in the EM classes that we have at UT is how we basically make electromagnetic waves. So, we have our tower or antenna, or what have you. This thing can take and make a time varying electric field up inside the tower or the antenna. That will in turn induce a magnetic field that changes over time. And this in turn induces another electromagnetic field, and so on and so forth. So we now understand that electricity and magnetism are intricately tied with each other, such that electromagnetic waves are basically these alternating fields of electricity and magnetism that propagates through space, and is actually inherent in the way that it propagates, that things go at the speed of what we call the speed of sound because of the interplay of these two fields, which makes that a sort of limiting factor of the speed of things in the universe. So let me know what y'all think. Let me know where y'all want me to go after here. Like, for instance, we can talk about the Coulomb force, some of the basic things we do. Awesome. Thanks, Darklight. And one of the things we might do is the Coulomb force, where we can have two charges and we can calculate the force between two charges. So let's say we have a positive charge and a negative charge. These two charges, depending on their charges and the radius between them, will exert a certain amount of force on each other. We have electromagnetic fields, which is basically in this form, and both of these decrease over a radius of r to each other. So why don't we go ahead and start with the Coulomb force? Let me know if y'all want me to jump to something else, or maybe we could do Gauss's law to find electromagnetic fields or something like that. But to use this simple example that I started with up here, let's say that this particle is charge Q plus, and let's say that this is charge negative Q minus times 2. And let's say that this is 2r distance from each other. So Lisa says, I'm glad to hear constant pain is trying to spirit. Glad it's getting better. Good and happy to hear another awesome stream of Dara. Awesome. I appreciate it. So yes, they say the struggle builds strength. So I could definitely see that. And I wonder, let's see if I turn this sideways if it helps. I'll have to change the focus of it. So I'll now just zoom in a bit. So we have these two particles. They're 2r apart. And we can actually get the force between these particles by simply saying, hey, that's actually a constant of the universe. So K is basically 1 over 4 pi epsilon naught. And this term here is basically the permittivity of fields through space. It's pretty interesting that there's a correlation between this and gravity. So if we look at gravity, Fg, we have the gravitational constant, we have the two masses, and divided by r squared. And the Coulomb force is basically in the same structure, still 1 over r squared, except we notice that there's two different constants of the universe involved, the gravitational constant and the Coulomb constant. So it just so happens that no matter what size mass we get, if we take two masses and put them r distance apart and measure the force between them, we'll always have this term G value between that needs to be included into the equation very consistently, no matter the size of the masses, no matter the distance. And the same thing happens with the Coulomb force. We end up getting this K factor. And this term here at the bottom is actually part of one of the things you can multiply together and get the square root of to get the speed of light. All of this stuff is very related. So for instance, if I was to apply this Coulomb force here and get this equation, we can say, for instance, the force between, if I was to call this Q1 and Q2, the force 1, 2 would be K plus Q negative 2Q over 2R squared. If we were to multiply this out with actual values, it'll get us the force between these things. And let me know if y'all have any questions or comments about that. Now, the interesting thing about these forces, at first we were sort of unaware of what was going on that caused these forces. At one point, people believed that there was basically some kind of particle or substance oozing between them, in a sense, if I remember right. But now we understand it to be fields, and this is where this comes in. So basically, if I have a positive charge here, we understand, and this is basically a convention, but we basically describe it as these positive lines or fields are emanating from the particle. And a field is basically a property that permeates space, that has an effect on things. Exactly. Action as a distance, action at a distance, Lisa. That's exactly what it was called. I thought it was action at a distance. But now we see it as fields. I guess it was almost like they were thinking of it as sort of like some kind of telepathy or telekinesis that particles are doing, this action at a distance thing. But now we understand that it's really um, these fields that are permeating space. And these fields, in a sense, uh, 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 permeate space and have an impact on things that are within that range. So, for instance, a common practice is to, let's say, use a test charge. And this test charge, let's say, will be Q plus. Usually the test charges are positive, but not always. And if I was to put this test charge next to this electromagnetic field, if it's a positive electromagnetic field, then the force on this particle will be away from the charge. Thus, we determine this particle as being positive because the force is going in the opposite direction. By the same token, by convention, I usually color the negative charge as blue and the positive charge is red, but I've seen a lot of books that do it the opposite way as well. Conversely, the field lines in a negatively charged particle are going inward, how we defined it. And if we were to take this same test charge and put it near this charge, the force, the Coulomb force on that particle, according to the equation that we did earlier, will go inward towards the particle. So to add another detail to the equation, we can say it's Q1 Q2 over R squared, and then R hat will give the direction of the force. And do you mean dark light, the action at a distance is strange, that sort of terminology that they had, or something about the properties of what's going on here? And I'll wait for your question. I know that there's a little bit of a time lag, and I'll respond to that. Now, one fun thing that I sort of enjoy doing now that we get from this is we can use something called Gauss's law to calculate the electromagnetic field that's coming from these particles that's basically causing these forces to be there. So basically, the property of these fields, if I was to, for instance, put a surface that can capture the fields around these particles. And let's say this surface is, I'll call this D or R. So the surface is R distance from the particle. And this Gauss's law will end up giving us the electric field at that point, at this distance R from the particle. And one thing that we notice is that the electric field is inherent in the particle. So there's only one particle there to give us this electric field equation. And from that, we can determine the electric field of whatever it is that we want to get the electric field of. So why don't we do an example? One of my favorite examples now, one of the ones that comes up a lot in the EM classes I help with, because I'm, some of you may know in my little intro slides that I put in my talks when I do a debate or whatever, I talk about being a learning assistant. And one of the common or classic problems is the electric field from a charged cylinder. So imagine that this is a cylinder of charge. And these, of course, have real world applications when we're building devices and things like that. And that's the interesting thing about this stuff. Like everything that you learn in the EM course these principles are actually applied to build. Like right now, you can see me on the camera because it's powered by electricity, and there's all kind of circuits and capacitors in the computer. We could talk about capacitors as well. And all of these things operate on these laws. If we didn't understand these laws, we wouldn't be able to build this technology. And we know, of course, that to bring up a common misconception in the burp world, we know EM doesn't have anything to do with gravity because it would be throwing off the technology that we have. It just wouldn't work. And Darklight says, "Yep, that's what I meant. Strange action at a distance. Quark, quark." Interesting thing, by the way, you had mentioned quarks. Just as an aside, uh, well, one of my last EM professors that I work with, he actually his research, I believe, is I don't remember what his research is in. We talked about how even if we have an electron, let's say this is an electron, like there's an inherent spin in the particles. Like the fact that this electron has a negative charge, there's an inherent amount of what they call spin in the electron particles. And it's because the electrons themselves are actually composed of, I remember right, 3 smaller particles. And the interesting thing is, like, these particles add up in such a way. Like, one of them might be an up one that has a 1/2, and one of them is a down one that has a 1/2. And let's say you'd have one more that has a 1/2. These numbers are probably off. And let's say one of them will be negative, and one of them will be negative, and one of them will be positive. And it cancels out so that the value that's left over is the precise value that gives us the electric charge of an electron. Like I don't remember off the top of my head what the number is, but the electric, the amount of charge in an electron, whatever it is in coulombs, its actual value comes from what's left over from the balancing out of the subatomic particles that make up the electron. So I've actually thought about going into research into quantum mechanics. I still may consider it. I'm still focusing more on astronomy, but we'll see how it goes. And by the way, my volume seems to be okay, but let me know if I need to address anything, make it lower or anything like that. So let's look at a typical um, problem where we're trying to get the electromagnetic field. So again, to set up what's going on here, the classical idea, and maybe I could have drawn it taller, but the classical idea is to simplify the problem because Gauss's law is based upon symmetry. So you want to have a system that's highly symmetrical in order to figure this stuff out. So let's say we have this cylinder, and I drew it taller because what I'm going to do is I'm going to consider it a tall or long cylinder so that we can sort of ignore the endpoints a bit because it's so tall. And we're going to say that we want the electric field at this point P, right there. So it's tall, it's symmetric, because basically the distance I have up to the top and the distance I have to the bottom is pretty much the same. And we'll say that this thing is charged with red charges. So there's a whole bunch of positive charges going through this thing. And let's say that it's a insulator. It's not a conductor, because if you have a conductor, all the charges are on the outside. It's a nice volume, Lisa. And Lisa says, I still think magnets are magic. They are pretty cool. And I guess we'll be getting into magnets a bit in the second half of the semester in my the class that I help out with. So I'm sure I'll make a video about magnets soon enough at least. So imagine that we have these charges. It's an insulator, so charges is distributed throughout the thing. So since charges are distributed throughout of it, basically we can say that it is a charge density or a charge. And actually, let me actually make it we should call it what doesn't matter. I'll just keep it a volume, so start it that way. So we have a volume of charge. We want the electromagnetic field there. So what we'll do is I'll imagine that there's a surface that's sitting like this. And what Gauss's law says is the flux the amount of uh, electric field going through that region is going to be the integral, an area integral, dot dA, and that's going to equal the amount of charge. In this case, it'll be a volume charge over epsilon naught. So basically, the volume that this thing is divided by epsilon naught, the charge that's enclosed, so I can put charge enclosed, will be the same thing as this integral, the electric field over the area, and the area is going to be the area of this imaginary surface here, the area around the charge. And this integral and this enclosed charge thing will actually give us the electric field that's going through there. And that's what we're looking at here. So if I was to look at the right side, we can say that we have a charge density. It's a insulator. So the charge is distributed through this entire volume. So this is basically charge per volume, right? And actually, let me actually put a Q here to make sure my notation is right. So the charge enclosed is going to be the density times the volume, or charge per volume times the volume, which is Q. So that's how we get that. So basically, we can say this is a charge enclosed, and this is going to be the volume, the amount of charge density per volume divided by volume. For everybody with me there. So another thing we could do on the left side is we can say that E, the electric field, dot dA, is the same thing as the magnitude of E times the magnitude of dA and cosine of theta. And the way this works is we can ignore the ends. So we're imagining that the field is coming out from this charge density here. And we know from earlier, the example earlier, you have a positive charge is radiating outward. And again, we're imagining this thing is very tall. So let's say the charge that's coming from here, it's sort of canceling out the charge that's coming from there. So we could just imagine that the field is basically, the net of it is only going straight outward. So the field is coming straight outward from there, and we can see that the surface that the field is going through is here, and the angle between these two things, normal to the surface and the electric field, is where we get our angle from. So since these are going in the same exact direction, the angle between these two is 0, and cosine of 0 is going to be 1. So that means that the left side, we can reduce it to E dA, right? So that means I have the integral of the area, E dA, equals the charge density times the volume over epsilon naught, right? So y'all can let me know if any questions or comments come up about what we're doing here. So this gives me the density of the charge inside the thing, charge per volume. This gives me the volume of the whole thing. This is the constant that we mentioned earlier. And this is the area of the, I'll make this a different color since I had that a different color there. This is the area of at P. So again, this is my point that I'm trying to get my electric field value of. So basically we're sort of adding up all the electric field that's coming through this entire surface at that point. That's what the integral is. And we're gonna add all that up and determine how strong the electric field is. And this is the electric field that we're trying to solve for. Now, the way we can do this is pretty simple. Like we can do a complicated integral here, which probably off the top of my head, I don't even remember how to do because we've been doing the shortcuts so much. But if I thought about it hard, I'm sure it'll come back. But all we have to basically remember is that the top part here is a circle, right? So that's going to be 2 pi r. So like basically if you have 2 pi, if you have a circle and we have a radius r. If you go out radius r and then go around 2 pi, that gives you the full, length around the circle, the arc length. And if I was to call this height, let's say h, I'll make it a little h to make it convenient. If I multiply that by h, then we have the area of that surface right there. So basically we're going around the loop, and then we're adding up all the loops that go on that entire height. So that gives us the area right there. That means the left side, if I actually take the integral over the area, that's actually going to be e 2 pi r h, right? And the volume of a cylinder, see if I remember that. But we know we're going to have 2 pi r h. That's only the outside. I'm gonna have to look it up. I don't even remember the volume of a cylinder. Let me look it up real fast before I try to figure it out and get the wrong volume. Right, volume of a cylinder. All right, so we have pi r squared h. I should have remembered. That's right. It comes back to me. So basically we have pi r squared. What this is going to be is the area of a circle. So the area of a circle is pi r squared. And then we have to multiply that times the height. So basically I'm taking the area of this whole circle here, the area of this top thing, and then I'm just adding it up as many times as it takes to equal up how many circles it takes to, basically I'm stacking up a whole bunch of circles on top of each other. And when I stack up all the circles h pi, that's going to give me the volume of that thing. So that's that. So that's pi r squared h. So now we have rho pi r squared h over epsilon naught. Now we're ready to solve for the electric field. So now I could cancel some things out. I could cancel this. Oh, and actually, let me make sure I'm specifying the radiuses here, by the way. So this r here, the right side is the actual volume of the charge. So this little r here, that's what this is. This is the r that says this is the radius of the actual charge. So we need that to give us how much area we have here, the area of the actual charge. So then we multiply the area of the actual charge by the height. This would give us the actual volume of the charge we're working with. And then we multiply this by the density. That's going to give us the amount of charge that's actually there. Right? Awesome, Catherine. Yes, it comes back when you work at it. Oh, and thanks, Lisa. I didn't notice you put the volume there for me. I appreciate it. So, yeah. But some of these equations, like, for the life of me, even I'm starting to remember the spherical one better now because we're starting to work with spheres more. I believe the volume of a sphere is what 4 third pi r cubed, volume of a sphere. But I don't know. Sometimes I probably sit there and work it out. I'll figure it out again. I need to remember how to do the integrals still. I remember when I took was it vector calculus, or was it calculus 2 or calculus 3? We had to actually do all these integrals manually, and I thought it was pretty fun. Like, we had to like get the volume of, let's say you had a sphere, but you needed to get the volume of only, let's say, the first quarter of the sphere. I guess technically the 1/8 of it, like the top half, but only 1/4 of the top half. It's a bad drawing, but you know what I'm saying. So I know it's fun, but I pretty much forgot how to do those integrals. But I would like to learn how to do them again. So we have this. So I have my density of charge. I have the volume of the charge itself, and that's why that r is this little r. And I'll put my point P at big R. So that means that I want the electric field big R away from the actual charge center, the center of the charge. So that's why big R is here. So basically we have going out big R, we're going around 2 pi at big R, and then we're adding up to h at big R. So that's giving us the area out where we want to get the electric field at. And again, we're ignoring the endpoints because we call this thing very long, and I'm getting the point right in the center. So so that's how that works. So what I could do is cancel some things out. So I would say I'll cancel the H's, I'll cancel the I, and we can say that the electric field of this cylinder will be the density of it, little r squared, over 2 big R epsilon naught. So this will basically give us the electric field at P if we had a number for the density of the charge, the radius of the charge itself, and how far away we want to get the electric field from. Which means we should be able to plug in any values and get the electric field for that. So that's how that works. I don't think I made a mistake. If I did, I'll just come back next time and point out any mistakes I made. But I'm pretty sure I did it correctly. Let me know if you have any questions about that, about getting the electric field from a cylinder charge. Now, I know there's a bit of lag. I'll wait for any questions, and I actually put the chat up so it can be seen. And so these things are very important. So there's a few more steps from this to get to a MRI machine, but that's what comes to mind. Like you have an MRI machine, even though that's mostly, I believe, magnetic, but still these principles play a part. I mean, there's like the interesting thing about an MRI machine. And Dark Light says, I have to eat, sleep soon. Finally, wishing you all the best. Thanks, Dark Light. Thanks for showing up and dropping a line. Good to see you. Lisa said, could you give a practical example of when someone would need to know the charge at point Q? Okay, awesome. Yes, so we'll go to a practical example right now. And even though I guess this is farther from necessarily the practical example of a charge at point Q, let me see if I could think of a more specific example of why we would need a charge at point Q. So let me think what comes to mind. Well, okay, this is a practical example and one that's more fitting. So we have computers, right? And one of my computers actually put it together. And if you were to open up your computer, you will see something called the motherboard. Thanks, Darklight. I appreciate it. I'll see you next time. Yes, it's very correlated. So, and this is how. If you were to look up your computer, you would see these things that look like this. They look like little bitty towers in your computer. Maybe that was a bad drawing. Let me try this again. They look like this, little bitty towers, right? And these are called capacitors. So what happens is you can have a battery. Like we're familiar with batteries. You know, you have a little battery that has, you put it in your whatever, and you have your positive and negative side. I might have mixed up the positive and negative. And let's say this is a double A. And what that does is it gives a certain amount of energy, you know, for a duration of time, then it runs out. But it's a very slow giver of energy. It gives energy over a long period of time at a very steady pace, very consistent, very needed. But there's some instances where we need bursts of energy, like we need a burst of energy very quickly. And capacitors can do this. For one, capacitors can store energy for a long amount of time, and they could deliver this energy very quickly. So when you see this little sort of stubby thing in your computer, if I was to blow it up, we're looking at something like this. And if I was to do a cross section of it, in the inside, you would see something like this. Like you would see it rolled up like so. Like this. And if I was to expand this a bit farther, what you would find is, and I probably should add another color there, but I'll give it more detail in a moment. What you'll find is that these are really two plates that are sort of rolled up with each other. And this is where your question comes in, Lisa, a practical example of why we would need to know charge, the amount of charge somewhere. So basically what a capacitor is two charged plates, and the electric field between these plates is what gives us its electric charge. So let's say if I was to call the yellow one positive and the green one negative, what happens is we actually use Gauss's law to get the electric field, and the electric field again it determines how much energy is in the thing. So basically, I'll take it in steps. So if I was to get the electric field from this thing, so again, I have a positive charge here. So this is similar to this charge, except this, oh my gosh, my thing is covered again. Sorry. So this is, basically what I did was I drew this right here. I drew the, basically a motherboard of a computer. This is the capacitor, the little tower thing sitting on the computer. And maybe what I'll do, I'll get better at that, I swear. Let me, you know what I'll do? Let me put the chat under here. So that way I can keep the chat up and I can keep the thing up at the same time. So we'll keep it like that. All right. So I drew the capacitor here. This is the motherboard of a computer. Right? Motherboard of a CPU. And, you could open up your computer without damaging it, just take the case off. You'll be able to see these little things. If I was to blow this thing up, it looks like a little tower. And if I was to cut the tower in half and look in the middle, you'll see a swirl. And if I was to unroll the swirl, you'll see these two plates. And basically you'll have something in the middle because if the plates touch, it'll discharge. So you can say that in between the yellow and the green, there's like a dielectric material that separates them. So I'll just put that there. Now we have a good working of but to make sure it's not confusing, I'll remove it from there, but there is something in the middle to make sure they don't touch. So let's say, for instance, that this thing is charged positive Q, and this thing is charged negative Q. I need to know how much charge is there, because if I was to take one of these plates, let's say I was to take the positive plate of the capacitor. So now I have a positive plate here. And actually, let me draw it like this. That's my plate. And this is my positive plate. What I can do is I can do the same thing. I can actually draw myself an imaginary surface and say, I want to get the electric field that's going through this surface. So if I was to draw it flat, let's say, I would have a surface that looks like this. And it's coming out the other side. So what's going to happen is I have my charge Q. This thing is charge Q. And this charge Q is going to be spinning out some field, electric field on either side. And if I wanted to get that electric field, I can do the same thing. I can say the flux that's going through the tops of this thing is going to be EDA, and it's going to be the charge of that surface, epsilon naught. So that's going to be EDA. That's going to be Q over epsilon naught, or actually A, QA over epsilon naught. So I think I mixed it up. Hold up. Q. There we go. So this is basically the charge on that area. The total charge is going to be the charge on the area times the area. All right, there we go. So now our area is going to be the circular area. And I remember earlier that's going to be pi r squared. And the area of charge we're dealing with is also going to be a circle on this thing. So that means that this is going to be equals sigma pi r squared. It's the same r over epsilon naught. And the thing about this is, remember I have one going up and one going down. So basically I'm going to have two of these, pi r squared, for the same charge, right? So basically I have E here and E here down. So this is going to be 2 E pi r squared equals sigma pi r squared over epsilon naught. And I could do some calculations here. The area is the same. And if I divide by 2, this means that my electric field for one of these plates is sigma over 2 epsilon naught, right? Now, since I have two plates together, that means that this plate is spitting out E equals sigma over 2 epsilon naught, and this plate is spitting out E equals sigma over 2 epsilon naught. So this gives me the electric field that's adding between these two, which is going to be E net equals sigma over epsilon naught. So whenever you have a capacitor, the electric field within the capacitor is going to be E is going to be sigma over epsilon naught. And this sigma is going to be the charge density, which we will be able to determine, like I saw earlier with the area. Once we get the area of this thing, we'll be able to know how much charge is there, which means ultimately we'll know how much energy this capacitor can spit out, right? So if we didn't understand this, we would not be able to put a properly sized capacitor in your computer, because if we put one too big and it spits out a charge of energy when your computer needs energy, it'll blow your computer if it's too big. Or we put one too small, you'll find that your computer keeps dimming or cutting off because it's not getting enough energy, and it wouldn't be working properly. So this is an example, at least, of why or how or why we would need to know the actual charge on something and how it will play a part in our everyday technology. So every time you use your computer, you're basically validating Gauss's law as far as getting the electric field, solving for the amount of electric field that's there, and the energy. One of the energy equations off the top of my head would be Q squared over 2C, and this C would be the capacitance of the capacitor. And that'll be another equation, but the capacitance, if I remember right, let me see if I can remember this one on top of my head. It should be, one of them would be epsilon naught A over D. So the distance here would be the distance between the two plates. The area will be the area. So that means that the bigger the area, the bigger the amount of capacitance. Just like you have a bigger cup, it holds more water. And the closer the plates are to each other, the more energy they hold. So this capacitance will deal with the energy, and all of these things are related. So this is a practical example that's every day related to the technology that we use. We can split energy. Matter of fact, when people have a, what do you call it, a defibrillator? It may not be the proper word, but let's say somebody's having a heart problem and their heart stops. And when they put the pads on them and they hit them with energy, that's a capacitor. That's a capacitor. Because if you remember what happens, I'm sure we've seen this on a movie, they charge it up. They say, okay, we need a capacitor. They hit the button and it's charging. And you notice they have to wait a while. And then when it's charged up, then they say, clear, whoosh, and then they hit the energy, right? So what's happening is they have the capacitors, and capacitors come in different shapes and sizes. I did a plate capacitor, but let's say you can have spherical capacitors. I don't, what the pads I think are usually circular, so they probably have an area capacitor, and these things are connected to a battery. So we'll say our battery is here, right? And actually, let's say that this is a switch to the battery. So all the time we see it, right? So when we want to charge the capacitor, we close the switch. Now these capacitors are getting charged. When it's fully charged, we end up getting a positive Q and a negative Q on the plate. So now they're fully charged. And, they say hands off while it's charging. They say clear, and then they actually open the circuit to the person. And I don't know the inner workings of it, but, there's another circuit that's actually, they actually just put the pads on the person, don't they? So they take and put the pads on the person, and then basically the energy that's stored up in the electric field. And that's how why the electric field is important, because the energy in the capacitor is actually stored in the electric field. The electric field that's going from the positive plate to the negative plate, that's where the energy is stored at. So they actually put pads on the person, and all the energy that's in the capacitor in the fraction of a second is deposited into the person, right? Exactly. It completes the circuit with the person. But you notice, right, after they do it again, they have to wait and charge it up again because that's how capacitors work. They charge up actually, depending on how much energy you want to put, they charge up pretty quickly. I mean, compared to charging up your cell phone, right? You charge up your cell phone, it takes, it could take a while depending on the size of your cell phone. But a capacitor, that's pretty quick, even though it takes a little bit of time. And it deposits that energy very, very quickly. It's like a dump of energy, right? And Catherine says, do you know what the plates and the capacitors are made of? Yes, that's a good question. They have to be actually conductors. So whenever you have a capacitor, it would always be a conductor. And the reason why is because when you have a capacitor, or at least when you have a capacitor, the charge is actually on the surface. So if I was to actually draw it out in detail, the charges, and I guess I mentioned it a bit earlier because I didn't detail it, but that's the reason why I have the surface here. So this is sigma, meaning a surface. Sigma equals surface density. And that's why when I did the surface, all I needed was the area, right? The area of this circle. And here, the area would actually be the area of the square, because this is the full area when you're actually doing it. But to do the equation, we pick something symmetrical to make it easy. If you look here, this was a solid thing, and it was an insulator, right? And that's why it was rho. So what happens is these are capacitors are conductors because the charge is actually on the surface of the capacitor. So all the charge is out here, and inside here there's no charges, and the charges are on the other side here, which may further explain why the electric fields come out both sides. So it always be a conductor, a metal, and ironically, the inner part of it would generally not be a conductor. So if I was to make this capacitor here, and I said that there's something in the middle to stop it from touching, generally the thing in the middle would be an insulator, would be a non-conductor. And what the non-conductor does is it allows us to adjust the capacitance of the conductor because the materials, even though the materials inside of it are not, since it's not a conductor, the electrons are not free to move. But if I was to take this insulator that's in between there and sort of give you an inside view of what it would look like, it basically has a whole bunch of particles that are, in different directions here. And let's say, usually they'll be balanced in some way. Like sometimes it can be because the actual particles themselves are imbalanced, but sometimes the electric field induces an imbalance. But initially, the charges are just any direction like this. Once we turn the electric field on, then the particles inside this thing, their fields align. So what happens is they start to point in the same direction. So if the electric field, as I drew it here, the electric field will be going in this direction from the positive to the negative. So the electric field will be going this way. So what will happen is all the negative sides of the thing will point to the left, and all the positive sides of it will point to the right. And this will have an effect in the electric field in various complex ways that allows us to adjust things. So therefore, we have a conductor on the outside and the insulator on the inside. And that's the way that works. Interesting. This is one of my favorite movies. It's been a while since I saw it, though. I can't say I remember the capacitor part of it. But yeah, capacitors everywhere, though. In computers, you know what they're with the metal, whatever they call that thing, defibrillator in hospitals. They're important, right? They pretty much any major circuit that you have, you will have a capacitor there. Because again, they can store energy, they could distribute energy very quickly. And they could even stop a circuit if you want, because if you put this thing on a circuit, once it's fully charged, basically is a break in the circuit. So they could be applied in many different ways. Yeah, Ed Harris is pretty cool. I saw him in Snowpiercer, which is an awesome story, and an awesome movie too. I'm pretty sure that was a movie, right? I know they made a series of it. Yeah, it was a movie with the guy that played Captain America. It was actually a good movie. I saw the series too. I believe season 3 is going to be coming out soon. I believe the writer's strike caused it to delay a bit. But yeah, it was pretty good. But awesome. But I wanted to give y'all some talk about some EM today, like I said, because I've been studying on my EM exam, which is going to be Tuesday. I still feel a bit uh daunted by it because it's some like I talked about how like the cooling force earlier, right? That's like basically in two dimensions where you have like F equals KQQ over R squared. And it's basically we're talking about just basically a two-dimensional plane. You have your XY thing, and let's say one charge is here and one charge is there, and you just have R. Let's say we're going into a three-dimensional realm, which is what we have to do in this class. So now we have this will be Z, this will be X and Y. And so now that I have a particle here and I have a particle there is not so simple. The radius here. So this might be, let's say, X, and this will be, let's say, I'll just call this X1 and X2 like they normally do. This would be X1 and X2. And what these will be is vectors coming from the origin, like so. So now instead of aura, now we have X1 minus X2 is going to be basically R, because now we have a vector that's going to make that point, and R hat. And R hat is going to basically be the direction divided by the magnitude. So let me see if I get this right. This stuff I'm learning, so I might definitely make a mistake here, but I'll see if I can write it out. Over R. So this is going to be the magnitude of this squared. So the magnitude of X1 minus X2 squared. And this is going to be R hat, which is X1 minus X2 over the distance of it, X2, right? Which means that this is going to be KQQ, and that was R hat. The magnitude of X1 minus X2 squared, actually cubed, if I absorb that, and then X1 minus X2. So this is what we're working with now in this class, like for the basic stuff. And everything gets worse from there. Everything gets worse from here. So we're doing electric fields in 3 dimensions. We're doing potential in 3 dimensions. So basically everything that I did here is basically, I mean, it's essentially a 2-dimensional problem because there's only the electric field is going in one direction, and we can calculate the potential between these 2 points. But what if you have like a spherical charge and then you want the potential, and it starts to get crazy. It starts to get ugly. So I'm going through it. We'll see how it works. I have the test on Tuesday. And exactly, that's what finding R as before. It's just now, instead of R being in this flat 2-dimensional plane, now the 2 charges are floating in space somewhere, and we want to get the force between those. So yeah, so basically what's going on is this line right here, this is X2, and this line right here is X1. So imagine that these are, and actually I could actually redraw it in 2 dimensions. I could just alternate I'll try to keep it pretty much the same. So if I was to turn this in this way, we can put it like this, and we can say that these are my 2 vectors is what they call it. So, and I believe I'll call the red one X2, X1, right? So basically now the distance R between these things is going to be this point between these 2 vectors. So to keep it the same way I had before, if I take X1 and watch what I do here, I'm going to subtract X2. So all I'm going to do, I'm going to put X2 here. I'm going to turn it around so it's going the opposite direction, and I'm going to subtract it, right? And now if I subtract that from each other, look what I get. I get the distance here And if I was to copy this distance and put it over top, you see that that is that. You see it? So now, in order to get the distance r, now it's actually going to be x vector 1 minus x vector 2 instead of simply, a distance on the axis, from each other. Like basically, I mean, this will get slightly complicated because you have, this is going to be a vector on the x and a vector on the y. But this is, simply, r equals the square root of x squared plus y squared. That's pretty, still a two-dimensional thing, right? That's just our regular Pythagorean theorem. But this, it becomes a bit more complicated. So that's how I got this right here. I'll delete this extraneous one that I was showing it with. That's how I get this equals x1 minus x2. And now this equals r vector. That's going to be my r now. And that's where this comes from right here. So basically the magnitude of this is going to be the magnitude of that radius. And it's the magnitude of that radius squared. So I have that squared. And this gives me the direction. So basically the direction x1 minus x2 is pointing down in this direction where this arrow is right here. And if I divide it by the magnitude of it, what it does is it gives me a little bitty arrow that's pointing, let me make it a different color or a different size to make it more clear, a little bitty arrow that's pointing in the same direction, but it has the size or length of 1. And this R hat basically gives me my direction where my field is going. So basically when I get this and I put all the values in, like let's say if I have a positive charge, Q, and I have a positive charge Q here and I put everything up, it'll let me know, for instance, the force onto this one is going this way. Like if I call this 1 and 2, the force of 1 on 2 is pushing it away. And this R hat here will give me that direction just by putting in all those values. So it gets a little bit complicated, but, got to do it. So because again, when we look at our technology, like I was going to talk about a MRI machine, these things are three-dimensional objects with a person up in there. But we have to understand the electromagnetic fields and the magnetic fields and anything that's going on. And basically what we're doing is we're using these fields to polarize the atoms in the person's physical body. And the MRI machine actually reads the polarization. And what happens is different tissues polarize differently. So bone will polarize differently from muscle, will polarize differently. And that's how they can look in your body and know this, they can see the shape of your brain tissue versus your bone because of the difference in polarization. Just like this material here, like when I say, well, this material polarizes in the field, our body does that too. But different materials polarize differently, just like how different materials they put inside capacitors, they use different materials for different reasons because they polarize differently. And thus they can see, oh, that's bone, that's tissue, because they can make an image of that. So all of this stuff is very much interrelated, and we use it every day, whether we realize it or not. So that demonstrates the veracity of it. Thanks, Lisa. I appreciate it. So yeah, I love to do this stuff. I love to talk about science and explain it. I actually do it for a living now, technically, because I work as a learning assistant in preparation to be a professor eventually. That's what I would like to do. So yeah, I'm glad y'all enjoy it. So it's my hour. I'd like to get a good hour into some good stuff. I'll be back next week to continue the talk, and we'll talk about something else then. Thanks for the well wishes on the exam. So I still have a few days to study. I'll be studying. I might take a break today though. I think I can use a break. So I'll probably take a break for the rest of the evening, and then come back tomorrow, all day tomorrow, Monday. And I'll try to hit it on Tuesday. So thank y'all for showing up. Thank y'all for dropping a line. And I'll see y'all next time.